Next, we're going to talk about fit and prediction accuracy for logistic regression models. This video will cover just fit statistics. Remember our donations example, where we're predicting whether someone donates and we're using age, income, employment status, and the number of dependents in their household to make a prediction. This was the R output for that model, and more specifically at the bottom, this was the fit section, the information about whether the model fits the data well. Unfortunately, in a logistic regression model, R squared is just not available. And the reason I've alluded to before, the errors are not the same. Our predictions are ones and zeros, and the truth is ones and zeros. There's no variation, there's no distribution of distances between truth and prediction. It's either right or it's wrong. And so because variation is measured in a different way, R squared can no longer represent the proportionate variation that is explained by the model. The way we think about R squared has to change. The fit statistics in this model fit section in the R output come from the maximum likelihood estimation process. AIC at the bottom is one measure of fit. For this model, that measure of fit is 2107.2. For AIC, it's important to know that the smaller the number, the better the model fits. You could compare 2107.2 to other models for this situation. So if I removed a variable or if I added a variable to this model, I could see, does the model AIC change and by how much? If the AIC gets substantially smaller, adding a variable would be a substantial improvement. But the AIC number doesn't mean anything on its own. 2107 means nothing. It's just that the smaller it gets, the lower it gets, the better. Another statistic is the deviance. Deviance is a measure of model fit also. And again, it's just one measure. It's not the only measure. Obviously, we've already talked about AIC, but there are lots and lots of other fit statistics for logistic regression. So here we have two measures of deviance. One is called null deviance and the other is called residual deviance. It's a form of the error, and again, smaller is better. It's kind of like the difference between y and y hat in a linear regression, where you have the actual minus the predicted, and that gives you an error. That's what deviance is representing. The null deviance is based on a null model that just has an intercept. And the residual deviance is based on the model you've estimated with the 4 predictors in it. And the idea is, if the residual deviance is a lot less than the null deviance, it means that you've reduced the errors by adding all those variables. So the null deviance is 4333, and the residual deviance is 2097. So you've cut the error more than in half by adding the 4 variables. So you're doing a great job, essentially. If the residual deviance is not that much smaller, if you go from 4333 to 4322, then you really haven't reduced the error by some substantial amount, and so your model is just bad. And that's how these fit statistics are used. The smaller the better. And for deviance, you want to be improving over the value of null deviance. And again, these statistics come from that optimization process that picks the value of the intercept and coefficients. Now, we're not going to do much with these fit statistics. The way that I like to measure the success or the goodness of fit of our logistic regression models is by prediction accuracy, and you'll see what I mean in upcoming videos.